Hello and welcome to our Unit 3 notes on the different bond types. We're going to review how to identify the bond types and what are some of the physical properties that are associated with each of the bonding types when they're present in a compound or substance. So we're going to start off with, there's ionic, which involves electrostatic attraction between oppositely charged ions. So the electrostatic attraction is the bond. There's covalent bonds, which involves a sharing of electrons, and we know that can be both equal sharing or nonpolar covalent, or unequal sharing, which is polar covalent. And then we've got metallic, which involves just metal atoms bonded to other metal atoms, and the metallic bonds are made up of delocalized valence electrons from those metal atoms. All right, so let's look at ionic bonding. So as you can see from the depiction here, we've got one valence electron, so this is your typical alkali metal. We've got an example here, a halogen, where it's got room to take in one electron, and so because of that exchange of electrons, we end up with a positive charge, a negative charge, and then again the oppositely charged ions are attracted via electrostatic attraction, and that is the ionic bond. So some characteristics, like if I have a sample of something that contains ionic bonds, I want to know what kinds of characteristics, what kinds of physical properties am I going to observe. So because there's this alternating pattern of cations and anions, there's a very strong attraction for, each cation is surrounded completely by a negative ion. So like these purple sodium ions are completely surrounded by the negative chloride ions and vice versa. And because of that maximized attraction, that's why we see the properties that we see, such as high melting points. So that's usually above 500 degrees Celsius. Again, there's always exceptions to everything, but generally ionic compounds have very high melting points due to their structure and all the attractions between or around each and every single ion. The other thing that comes from this structure is that the solids are hard and brittle. So I have a little quick animation to show you about why they would be brittle. And so let's just take a look at this. And so notice we're going to show there's the alternating pattern, and we're going to see it hit with a hammer. And we'll pause that. So you can see that, if we try to, if we strike an ionic compound, as soon as there's a shift, because of that alternating pattern originally, we shift the ions a little bit, we end up where we get to a point where the positives and negatives are actually lined up with each other. Well, obviously the like charges are going to repel, and as a result, we see the solid then breaking apart easily. And I think if I continue on the animation, we'll see that happen. But again, those like charges are going to repel, and so that's the reason for the brittle nature of the ionic solid. And back to the notes. All right, they dissolve in water very well due to attractions with the polar hydrogen and oxygen ends. So obviously the H end of the water molecule is partially positive. That is available to attract the negative ions. The oxygen end of the water molecule is partially negative, and that's there to attract the positive ions. And again, we know that there's some limitations to solubility based on especially the strength of the charge. But nonetheless, there's that capability of forming attractions because water is polar. And then we've got the positive and negative ions. And again, we know that when ionic compounds do dissolve, even if they only dissolve a little bit, the case is that they're going to dissociate. So they're going to break up and the ions are going to separate because the positive ions go off and intermingle with the oxygen end of the molecule, water molecule, and the positive ions go off. The negative ions go off and mix with the hydrogen end. So again, that's why they're separating, going separate ways. And as a result of that, we refer to them as electrolytes because those solutions containing ionic compounds can conduct electricity. And ionic compounds can also conduct electricity in molten form. And that's because if we don't have the solid structure, the ions are free to move past each other. We're going to see that capability of, if charged particles can flow freely, electrons are also capable of flowing freely, and that's what we see in both of these cases where we see them conducting. So when they're dissolved, they can conduct electricity because the ions are separated, and likewise charged electrons can pass through the body of the liquid, and also in the molten form. So molten is just referring to, of course, the melted, but if we're talking about super high temperatures, that's why we're calling it molten and not just a liquid. All right, and they do not conduct electricity as solids. So if you need the freedom of motion of charged particles, you don't have that with the solid. So that is why they don't conduct in that state. Okay, then we've got covalent compounds and their characteristics. So there's attractions of the electrons for the neighboring nucleus. So obviously an atom's own electrons are attracted to its nucleus, but they're also attracted to a neighboring nucleus. So that balance between those attractive forces are what hold the two atoms together and forms a covalent bond. Covalent compounds are not going to conduct electricity as either solids nor when they're melted, so it doesn't matter. Now again, there might be a few exceptions somewhere along the line, like in the carbon allotrope, graphite, for example, but that's, in general, not what we're going to see with covalent compounds as a physical property. Solubility is dependent on the polarity of the molecule. So, polar molecules will be soluble in water. Non-polar molecules won't be soluble in water, but will be soluble in other non-polar substances, and we'll study those intermolecular attractions later on in the year. But again, solubility is variable depending on the polarity of the covalent compound and the molecule shape, which is what we'll be getting into this unit, and also what type of substance you're mixing it with. So it has to be polar to dissolve in water and so forth. There's variable hardness, so again, it's going to depend on those intermolecular forces, which we'll address later on down the line. And there's a wide range of melting points, again, because of that wide range of intermolecular forces. So it's not like the ionic compound that was, just held together by just this extreme, full-on positive and negatives attracted to each other. There's some shifting of electrons. There's some, varying ranges of polarity that's going to hold molecules together and require more energy to separate them than others. So that's why we're going to have a varying range of melting points with covalent. Electronegativity is going to be something that we use to help us pinpoint or predict the type of bonding present. But again, just like everything else, it's not a hard and fast rule. So electronegativity, we should know, is the ability of atoms in a molecule to attract electrons to themselves. And here is the chart that gives us the layout. So in general, we have electronegativities increasing left to right, decreasing top to bottom. This follows that same trend of ionization energy, although notice we don't have information written here about the noble gases, and we would have information for ionization energies for them. But so electronegativity, again, we're studying how do atoms compare when they come up against one another in terms of sharing electrons with one another. So this is a ranking system. The values go up to 4. Again, you might see a slightly different scale reported elsewhere, like in the activity that we did. But in general, we say that fluorine's the highest, maxes out at 4. And again, we can use this to predict how things are going to bond. And the other thing to note is that, again, that electronegativity trend, very similar to ionization energy trend. And that's because of that, as we move left to right across a period, the nuclear charge increasing pulls in not only the valence electrons of the atom itself, but also then can attract in neighboring atoms because they can get closer as you get further to the right. And as you get further to the right on the period, the atoms over on the right-hand side, can allow neighboring atoms to get in closer to their nucleus and actually are then able to pull in the electrons from neighboring atoms. So there's your trends. Okay, so let's take a look at, just to clarify again, the difference between electronegativity and electron affinity. Read the choices. You can pause and give your answer. And the answer is going to be B. So EA is electron affinity. That measures the energy released, or technically can be the energy absorbed too, if it's not favorable. Electron affinity can be positive as well. But so that's the measurement of the change of energy in taking in an electron for an atom. Electronegativity is kind of a ranking of the ability of the atom to attract electrons to itself. So that's the difference. So one's an amount of energy. That's the electron affinity. Electronegativity is kind of our ranking system. All right, so we're going to use that in differentiating ionic and covalent bonds. So, we've worked through, the more complicated method of predicting bonding in our initial worksheet, but typically we can get a pretty good estimate based on just our electronegativity differences. So again, typically very large electronegativities, we're going to see ionic bonds. That would mean that one atom is pulling on electrons so much more strongly than the neighboring atom that it can just take the electrons away. So that's why we'd have then a transfer of electrons and then the two ions sticking together. So that's why we see metals bonding to nonmetals and forming ionic bonds typically. There are exceptions as always. So again, this is kind of on a spectrum. Obviously, if metals are all the way through the center of the periodic table, there's going to be a range of electronegativities that are getting closer and closer to the electronegativities of nonmetals. And so you start to see a little bit more closeness there, even though you've got a metal potentially bonding to a nonmetal. So some examples of exceptions we should look at here. And really what it's going to come down to is if we can try to make predictions, but if we look at the physical properties of a substance, that's really going to be the deciding factor of, is this ionic or is this covalent? So, if you look back at the previous slides where we talked about the properties of these substances, that's what you would really need to use if you had something available to you to test. That's what we would want to do to confirm. So if I look at our example here, this tin 4-chloride is actually a molecular substance that is a liquid at room temperature, has a very low freezing and/or I guess we would call it a freezing point rather than melting point because it's that transition is happening lower than room temperature, boils at 114 degrees Celsius. Electronegativity difference, though, is 1.2, which would make it identify as a polar covalent substance. So, tin is a metal, chlorine is a nonmetal, and so if you just looked at that, you might say, oh, well, maybe that's ionic. But again, we see from its properties that it does appear to be exhibiting characteristics of a molecular substance. Ionic compounds are going to be solid at room temperature. This is not. And so anyway, if you actually then look at the electronegativity difference here, you can see that they're actually fairly close, and that's why we see that molecular covalent bonding rather than ionic. Also, another thing, so this is a very important little tidbit to have in your back pocket, that when metals oxidation numbers increase, so like +4 and above, that's when we start to see metals participating in covalent bonds. Meaning, like when I look at this, manganese 2 oxide, that exhibits characteristics of an ionic compound. In that case, it would have a +2 charge, and we find, especially with these transition metals that can lose a whole bunch of electrons, more than just 2 or 3. What's happening is that they may lose some electrons, but it is actually pretty hard to give up more than like 2 or 3 electrons. And so we notice that there may be a loss of a few electrons, and then the metal ends up, instead of giving up more electrons, it actually starts participating in sharing the electrons that it has remaining. So that's what we see when we look at like the permanganate ion, which is one of those polyatomic ions that we know and love. And if you look at manganese here, its oxidation number is +6. Likewise, when we look at this example, manganese has an oxidation number +7. In those cases, that's manganese actually participating in covalent bonding. So your general guideline is that there are some cases, especially with the transition metals, when we're getting to a +4 and above oxidation number, you may more likely see that metal participating in covalent bonding than ionic. So that's a good thing to have in mind. All right, so again, looking at data, looking at properties that can be tested, we want to take that information and then relate it to our predictions. So we have a yellow solid that melts at 41 degrees Celsius, boils at 131. There's a green solid that melts at 2320. We're told that one of them is chromium 3 oxide and the other is osmium. So the osmium 4 oxide, no, osmium 8 oxide. Which one would you expect to be the yellow solid? So pause and answer. And so the yellow solid that melts at low temperatures, that clearly is describing something that is most likely covalent, and the 2320 is most likely ionic. And again, both of these have a metal with a nonmetal. Both of these have a metal with oxygen. However, the osmium has ridiculously high oxidation number. Chromium has, a relatively, not so bad, chromium +3. So we would predict that B would be that ionic green solid at 2,320 degrees Celsius, and the OSO4 is probably going to be that yellow solid. And again, that's based on that tidbit that I just said would be useful to you. Wasn't that useful for this question? See, I told you. All right, so A would be what we would predict to be that yellow solid based on that fact that having such a high oxidation number is unlikely that we'd see that exhibiting ionic bonding. All right, and then we've got metallic bonds. So this is where we've got our positive metal ions. So they're metal atoms, but because of the attractions of the valence electrons for the neighboring atoms, there's this delocalization of electrons where these are representing aluminum atoms, and so these 3 valence electrons that we have for each aluminum atom, they actually they're kind of attracted over here and they're attracted to the original atom. So those collectively as a whole, this body is neutral, and there's no positive charge overall, there's no negative charge overall. The electrons are still in the structure, so they're not leaving and forming an overall positive. But again, electrons are kind of loosely held and sort of pass from atom to atom and between them pretty easily. And so that's that metallic bond that, again, this attraction of these electrons for this atom and this atom and this atom and this atom, that's what's sort of holding the atoms in close to each other. And that's what we mean when we describe metallic bonds. So properties of metals, good conductors, and that's because of that free movement of charged particles throughout the structure. Their melting points actually range. We saw pretty low melting points for the alkali metals, and obviously for mercury, which is a liquid at room temperature, and very high melting points. They actually kind of max out around tungsten. So like in the bottom middle of the D block is where you see the maximum melting points. And other properties of metals, they tend to be malleable, ductile, and lustrous. And that all comes down to these free-flowing electrons as well. So let me just shift to a little video here for you just to show you that. Let's check this out. So again, the reason that metals are shapeable and malleable, so unlike what we saw with the ionic compound, notice that those atoms being pushed, right, or the nuclei being pushed, they, because we still have this sea of electrons that, are kind of holding everybody together, we don't see that same, there's not all of a sudden any difference in this structure versus like what we saw with the ionic, where the like charges were lined up, and that caused parts to repel apart. So again, it's because of this uniqueness to the way these metal atoms are being held together, the way the metal cations are being held together with their valence electrons, that allows them to be reshaped without breaking apart like we saw with the ionic solid. All right, get out of that. And lastly then, if we're talking about metals, then the structure of alloys comes up a lot, because a lot of times we need to take the characteristics of a metal, but maybe improve it a little bit for strength or improve it for whatever particular purpose. And so alloys are typically metal mixtures, or can be metals with a couple different types of atoms mixed in. Some non-metals sometimes, or sometimes it's just a mixture of metals themselves. But what the characteristics are, what the sizes of the atoms making up the alloy, that has an impact on the properties of the alloy. So just to show you some vocabulary here regarding alloys. So obviously there's pure metal where all the atoms are identical. Then we've got a substitutional alloy. So if you just look at the picture, when we have a substitutional alloy, you've got, instead of every atom being a particular metal atom, you have substituted in, so taking the place of. So a substitutional alloy has another metal atom, or another type of atom, taking the place of the main metal atom in the metal. And so this allows it to maintain malleability and ductility. Typically, we're going to see atoms that are around the same size replacing in a substitutional alloy, so that's something useful to note. And then our other type of alloy is interstitial. So interstitials, we've got something in between spaces. That's what this word is kind of referring to, or should remind us of. So we usually have, in this case, an interstitial. We've got a smaller radius atom substituted, or not substituted in at all. It's fitting in between the little spaces, essentially. And because it's a smaller atom, it's able to do that. And as a result, that allows the alloy to have increased hardness, but it also then reduces that flexibility. So obviously if you want to maintain your ductility, malleability, you would probably go for a substitutional alloy. Interstitial, though, can increase hardness, so that reduces the flexibility of moving these atoms around. And then here's obviously a picture of the two if you combine them together. And so that is it for the general characteristics of our bonding types, and we'll do more work in class with predicting them and then comparing properties of them as we go.